So I saw this experiment online. It's basically how to hypercharge glow-in-the-dark stuff. I have here this alarm clock that is a radium clock, so the glow-in-the-dark stuff is zinc sulfide, and the rest is a flash circuit with a xenon tube and a mirror for concentrating the light. The flash circuit is the xenon tube, an IFK 120 Russian xenon, and is connected in parallel to an electrolytic capacitor, high voltage electrolytic capacitor, 470 microfarads. This gets charged to like almost 300 volts. To ignite the tube, there's a piezo igniter here on a push button assembly. And to charge the capacitor, there's an isolation transformer and a resistor 1.5K, but not important, and a diode for providing DC, and a multimeter for reading the voltage for the charge. The point is that radium clocks almost never shine in the dark. Why? Because the radium in the compound destroyed almost completely the zinc sulfide, the glow-in-the-dark stuff. So in fact, as you can see, I can charge it under my desk light. Try to charge it, turn off the light, and almost nothing. I see nothing. Okay, so let's try with the xenon tube. So the capacitor is charged now. It's like 290 volts DC on the capacitor. Let's unplug the transformer because I have bad experiences with piezo igniters and mains. Okay, let's turn off the desk light, finger on the piezo igniter, and yeah, okay, it lasts little. The exposure is at maximum at the moment on my smartphone. Okay, again, max voltage or almost. Let's unplug it. Desk light off. Finger on the igniter. And yeah. $40 volts remaining. Okay, now something a bit less vintage. It's modern glow-in-the-dark stuff, powder and glue. And I'm not sure if it's strontium aluminate, but probably. Anyways, capacitor charged, 300 volts. Let's unplug the system for safety concerns. Turn off the desk light. It's already a bit charged, but not as much. That's pretty fast. Yeah. So after getting this scope here, I wanted to try some experiments with the XY mode of the scope, because cathode ray oscilloscopes are usually much better for the XY mode compared to digital ones. And I have here some circuits, some DIY, some pre-made like an Arduino, to do some effects for the XY mode, and I'm gonna show you now. Okay, the first test is oscilloscope music that you probably already know. It's basically just a stereo sound music coming from a source, and this goes both on the oscilloscope on the two channels, y-axis and x-axis, and an audio amplification system. This is a power amplifier, just a power amplifier for this speaker. A bit of volume. Okay. And it's a nice music. I like this this genre actually, and the result is amazing. It's both sound and video on the same track. That's super cool. And I have this setup here with an audio source, preamplifier for the x-axis. This is the x-axis here on these banana posts here, because the x-axis is here and it's a bit deaf and it needs a small preamplifier. 12 plus 12 power supply, 12 plus 12 volts power supply, maybe an overkill for this task, but anyways, and that's basically it. And this is the result. This is super cool. Look at this robot. Okay, dark. Much better. That's so cool. And I actually like this music. This is my genre. Look at this. Okay. Another cool test to do is to draw custom shapes and drawings on the oscilloscope with the kinda sound, again, same setup of before, same preamplifier for the x-axis for my scope, because mine needs it, and powered by the 12 plus 12 volts stabilized power supply, audio source, and this is the result. Nice. Oh, wait a second. This isn't my girlfriend's face. Wait a second. I don't have a girlfriend. Wait a second. This is maybe the reason why I don't have a girlfriend. Oh, anyways, I'm gonna show you how to do this now. To do that, you have to go to the website I link you in the description of the video below, and there you can draw freehand your figure with the mouse. Like this, and once you release the mouse, it will play automatically from the website a sound out of your PC, and you have to hook up your scope to your PC, to the audio output, and it will draw the figure on your scope, but it will do this just once every time you draw there. But I don't do that, especially because I don't want to hook up too many things together. So once the sound has been played, you go to page properties or page informations, media, and you have to locate a ghost audio file like this. Select it, save it, and give it a name .wave, and save it. This way you can have a wave file that you can play in a loop through the phone or device, I don't know. Okay, now something completely different. This is a clock called sometimes Oscillo clock, and it's made with just a microcontroller, in this case an Arduino, a Leonardo in my case, but you can use the Uno. You need the sketch. I link you in the description of the video the original source for this project, and you need the Arduino and basically a stupid filter circuit for the PWM out of the Arduino, power the Arduino with 5 volts evidently, and this is the result. That is quite cool. You don't need the preamplification or anything. And yeah, it's a bit slow, honestly, but you can take pictures of it with a longer exposure and it will look really cool. And it can move with this button or using an RTC on the Arduino. The sketch provides it. And it moves. I don't know if you can see the minute's hand move fast. But anyways, let's correct a bit the exposure. Okay, now it's a bit better. There's a bit more of exposure. Let's try to adjust the... okay. Much better. Now you can see it almost perfectly. You can see the second's hand move. That's pretty cool. I'm varying the brightness of the scope. Now there's much more persistence. Yeah. Okay, now something again cool. This is a video sync separator. It's a circuit with like 3 transistors and a bunch of analog components. I have an analog video source, a camera, a PAL, video composite video. And this circuit separates the brightness channel, the vertical ramp, the horizontal ramp, and the 2 ramps go on the 2 channels of the XY system of the scope, and the brightness go on the Z channel on the back of the scope, because the scope has the Z channel. And this is the result captured by the camera. This is my hand. I have 2 of them front of the camera. And yeah, you can use the scope as a monitor. Actually, the colors are swapped, are reversed. The brightness is reversed, so you maybe have to invert the signal on the source somehow if you have a PC or something. But anyways, this is it. This is the circuit. And I'll link in the description of the video the original source of this circuit here. But my subscribers always ask to me, why don't you throw yourself off? Why don't you make one of those awesome Indian videos about electronics and projects? That's a good idea. So I needed a low power, low voltage ZVS driver. Why? Because if I want a low power out of a ZVS for various reasons, I can't use a classic ZVS driver pre-made or DIY, because classic ZVS drivers need at least 12 volts to operate, and at 12 volts they are already fairly powerful and sometimes also dangerous. They maybe can operate at like 8 volts or 10 volts, but maybe badly. So maybe I needed, for instance, logic level MOSFETs to make a ZVS that operates at low voltage. And I used these MOSFETs here that are SOP8, and I modified them to stick them to an heatsink. and these are just 60 volts of maximum voltage, so the driver can be used up to like theoretical 18 volts. Anyways, other differences from other ZVS drivers is, for example, the tank capacitor is smaller, and this in conjunction with a higher inductance on the primary or coil to have a higher Q on the circuit and draw maybe less current and be less powerful. And another detail is the diodes, the feedback diodes. These are not the maximum voltage for this size of diodes, because if you use a UF 4007, that is 1 kilovolt of voltage, that has a fairly high voltage drop, forward voltage drop. But if you use the 400 volts or 200 volts or 100 volts diodes, they have a lower voltage drop, and the feedback system will work better at a low voltage and logic level MOSFETs. And these MOSFETs anyways have been chosen to have a low on resistance, RDS on, because the feedback of a ZVS driver depends a lot on the ability that the MOSFETs have to close really well. Okay, now let's try it. Let's draw some arcs. Let's power it at 4 volts DC and drawing just above 100 milliamperes, but without arcing, because it will be like 1.5 amps arcing. Let's draw some arcs. It doesn't even look like a ZVS driver. Monstros. Okay, yeah, I tried touching it and it hurts. It hurts. Okay, now let's see the result on some gas tubes. Let's power it at 3 volts DC, just 3 volts. Let's see with a neon tube. This is an AC flyback. Okay. And CFL tube. Yeah, it's capacitively coupled to my fingers. Okay, let's try 2 volts, not to 1 volt. Oh, come on. 2 volts. Let's try again with the neon tube. And it works down to 2 volts. Two volts DC. So I tried and at the end succeeded at taking out the most out of a washing machine IGBT to make a Tesla coil. And you may think, why insisting with this kind of transistor? Well, because these are fairly easy to find. You can find 6 of these in every inverter washing machine that is a kinda late model, but not too much. And the rest is basically just trash. So you don't need to buy even high power MOSFETs or things like that. The circuit in this case is quite simple. It's just a so-called MOSFET Slayer exciter, or sometimes even a Russian Tesla coil. And the only particulars are that I used an external capacitor on the gate of the IGBT, because the gate of this transistor is very low in capacity, so it can make some noise on the primary and make flashover between the secondary and primary. And this is a 800 picofarads capacitor between gate and ground. There's a interrupter potentiometer to adjust the triggering point on the half wave. And as protection for the gate, I used a transient voltage suppressor here on a full bridge rectifier made with 4148 diodes. And that's basically it. So, to obtain the maximum performance for the coil, I used a staccato controller here that makes 5 Hz out of the coil, and this to avoid overheating of the IGBT. This is powered by this, let's say, small transformer, and initially I used this transformer also for powering the whole circuit, but this transformer can't make enough current, and what happened? It happened that when using the 100 volts SC output, these capacitors here, the bypass capacitors, got charged a lot with an open circuit voltage, and when the staccato triggered, the circuit received a really big shot of power, and this broke the first IGBT that I used. So to solve this, I used instead a Revundo MOT here. This transformer is 230 volts input and 115 output. So this makes much more current, so I can make bigger arcs without pushing too much the open circuit voltage. So the transistor is, let's say, safe. Okay, let's try this thing. Anything is set up and adjusted, also the variac. Okay, staccato controller on. Here. And power. And this is the result. This is, in my opinion, the maximum. Sorry. Okay. Okay, we are at 82 volts SC. That will be more than 100 volts peak. The sparks are like, I don't know, 15 centimeters, maybe more. Okay, and you can also simplify it with just one transformer for the main power. In this case, we have the smaller transformer at theoretical 72 volts SC, that will be 100 volts peak, and no staccato controller, just the interrupter knob, and this is the result. At 50 Hz, no staccato. Yeah, the sparks are shorter because I can't push the open circuit voltage with this transformer. Just shots because I don't want to overheat the IGBT. But anyways, yeah. So thanks for having watched my video, and bye!